Sri G. Ilongovan, distinguished scientist, has been taken over as Chief Controller R&D R&M in DRDO headquarters on 1st April 2007. He graduated from Tyagarajar College of Engineering, Madurai with the BE in Electrical Engineering in 1972. He then obtained his MSc Engineering in Applied Electronics during 1974 from Ph.D. College of Technology, Coimbatore. Thereafter, he joined ADE DRDO in the year 1975 as a junior scientific officer and was part of this avionics flight simulation division. During his 32 years career at ADE, he has successfully executed a number of system-related projects. He was project director for a number of simulator projects, including LCA Engineering Simulator, Avionics, Partas Trainer, and Computerized Pilot Selection System. He has graduated step by step from a design engineer to technology division leader to system designer to a number of simulator projects to corporate manager, heading a lab as a director, and finally as CCR&D in DRDO headquarters. He is a fellow of IETE. He has been awarded the 4th IETE BV Baliga Memorial Award in the year 2001 and was one of the recipient of DRDO Pathbreaking Research Outstanding Technology Development Award 2002 for the contribution in digital flight control system for light combat aircraft. He received the Agni Award of Excellence 2005 for the development of computerized pilot selection system. And he's the father of the India simulator. So may I request Chairman to conduct this session, please. Thank you.
Good morning to everyone. In this session, we have 4 eminent and distinguished speakers. And the theme of this session is technology, innovation, and planning. In fact, I am privileged and honored to chair this session. And definitely, I must thank the organizers for giving me an opportunity to participate in the seminar. None of the speakers really require any introduction. All of them are well known in their own respective areas, but still it is a customary to have a formal introduction of the speaker. So I will try to be as brief as possible, because if I start reading the biodata, which runs into pages, it will be really difficult. The first speaker is Dr. Jonathan P. Howe. He is a professor from M.I.T. He received his bachelor's degree from the University of Toronto in the year 1987 and completed his Ph.D. from M.I.T. in the year 1993. Subsequently, he did the postdoctoral work on the middle deck active control experiment that ultimately flew in the Space Shuttle Endeavour in March 1995. So before joining M.I.T. as a teaching faculty, he worked at the Stanford University. He guided a number of Ph.D. students and worked almost all the areas of the UAV. He has received a number of awards, and he was a recipient of the 2002 Institution of Navigation Burka Award, and he is a fellow from M.I.T. Aero Astro Department and associate fellow of the AIA and senior member in IEEE. May I request Dr. Howe to talk about realizing a fully autonomous UAV systems, what are the challenges and the issues, and how to resolve them.
And, welcome, everybody. Good to see everybody here, and thank you for the organizing committee for inviting me to this wonderful conference. So what I'd like to do today is talk to you about realizing fully autonomous UAVs, both the challenges and issues that are faced in the future. And as indicated, my name is John Howe. If you're interested in talking to me more about this, I'll be here most of today. Perfect. Good. Hopefully you can still hear me. Send me an email if there's any questions, and hopefully there will be, and hopefully this will be somewhat entertaining, get everyone woken up in the morning. I'm still a bit sleepy. It's about 4 in the morning. So, introduction. So in terms of UAVs, I think everyone's aware that UAVs offer a new paradigm for executing a bunch of different missions, numerous tasks. There's the dangerous, dull, and dirty discussion that everyone's had now for probably about a decade, But the point is that the vehicles themselves are more tolerant to much higher risk than is traditional for manned vehicles. In terms of the actual operating cost, it's quite possible that by removing the humans from the actual execution, you can reduce the cost. But in terms of the new sort of green initiatives that people are interested in, it's also possible that the UAVs, in terms of enhancing the flight control and also doing the planning for the actual vehicle motion itself, it's conceivable one could reduce noise pollution and emissions. In terms of actual sort of execution, there's the potential of just faster response to faults and failures, and so as a result, you end up with a potentially safer vehicle. So what I show here is just a bunch of possible missions. I chose to focus on the ones which are civilian, but I think everyone's aware that there are many military ones as well. A couple that are shown here that have been of interest in the U.S. is essentially asset control, so you're looking at pipelines, borders, nuclear power plants. But shown up here is also one of the UAVs that NASA is using for its forest fire protection and identification. And then on the bottom right is actually the agriculture detection that was used in a mission, actually in the coffee fields, which is something that's close to my heart, given the amount of caffeine that I drink. So those are the kinds of things that people are thinking about in terms of the use. But I think everyone's well aware that, I mean, when you fly on commercial vehicles, the airlines, there's a very, very sophisticated control system that are executed on those. High degree of computation and autonomy and control that are on board these vehicles. But of course, there's always humans there in the loop that can do the override. So when we start talking about UAVs without the manned component, then obviously it's a slightly different animal. But it is true that the flight control for these UAVs is also quite sophisticated. And again, I come from an academic perspective, so what I listed here was just some of the devices that I would tend to think about. But there's three companies here, the Micropilot, CloudCap, and Proceris, which are devices you can go and buy. Very sophisticated autopilots from the perspective of takeoff, cruise, and landing. Quite capable, fully functional. And I think the Micropilot there is showing about 28 grams. Everybody's competing to be the smallest, either the size of a quarter or the weight of a quarter, whatever it is they're trying to accomplish. But the point is, for very little weight, you can actually get a fairly sophisticated device. And of course, you've probably all seen the Parrot, which is, you can buy them in just about every airport now. And basically, it's all the rage with the kids. And basically, it begs the question, you know, at what point will it become, essentially, everybody will have one of these Parrots, and UAVs will be ubiquitous. It'll be everywhere, just flying around at every mall. And so this notion that, you know, maybe UAVs in the flight space is some time away. I think when you see things like this Parrot flying around, it's really not the case. I think that it's going to be very soon. And we'll have to address these issues of how do we handle the fact that these UAVs are here and flying. But to achieve many of the goals that were listed on the previous page, there's an increased level of autonomy that's going to be required. The flight control is not enough. You know, takeoff, cruise, and landing is insufficient. There's a bunch of other things that need to be addressed. And that's really the purpose of this talk, is just to talk about how we actually get there from here. Excuse me. And there are a bunch of challenges. There's technical, logistical, and legal. I can talk to you about the technical, somewhat about the logistical, and not about the legal. That's not really what I can really comment on. I can give you some indication of my kinds of thoughts on it. But let's talk a little bit about levels of autonomy. When you go out in the literature and take a look, there's a bunch of different definitions. So this is okay, that's worse than I thought it was going to be. So these were designed as somewhat eye charts. You're not supposed to read them, just sort of recognize that they're there. This is Tom Sheridan's list of the 10 sort of levels of autonomy that were given, basically 1 through 10, where basically the computer's not really in the loop with 1, and all the way up to 10 where they are. NIST then did a report where they went off and looked at it, and they came up with their Venn diagram, a different eye chart. But the one I wanted to focus on, which hopefully you can see, is the one that Suresh and Professor Ghosh had done, which was thinking about their 10 levels. Unfortunately, they go the opposite direction to Sheridan's, but this was from their paper, so I just cut and pasted here. But the point was that the first 4 or 5 focus on single vehicle autonomy, and then after that you start getting to the multi-vehicle autonomy. So many of the missions that we're thinking about actually involve having multiple UAVs. And so we'll address some of the issues that have to do with levels 0 through 4, and then move on to thinking about 5 through 10. So the technical challenges then, and again, I have to apologize that I do this from the perspective of someone in the U.S. I think many of the challenges are the same the world over, but when I start talking about the national airspace, I'm thinking about the national airspace in the U.S. But one of the key steps then is just developing technologies that will enable fluid operation of UAVs in the national airspace. So when you talk to people at AFRL, the sort of the wording they give is same base, same time, same tempo. They just don't want something which is so different to operate. Now, it is conceivable, and I have friends that have done this, that you can go to the FAA and apply for exemptions. You can either do it by what's called a COA, or you can get an experimental exemption. But the process isn't particularly easy. I haven't done it for that reason. And the result then actually will be a set of restrictions that are typically quite cumbersome. By cumbersome, I mean you have to have basically safety pilots, flight vehicles that are following around your UAV if it goes outside of line of sight, and basically health checks on your safety pilots that rival the level of health checks you would have on a pilot if they were in the air. So quite cumbersome to do. Not impossible, but cumbersome. So these are the kinds of challenges that we have to sort of find ways to overcome and sort of try to meet the FAA in the middle in terms of what it is that they're trying to accomplish. So one of the major challenges, and when you work with robotics, and again, UAVs is just one of a robot, one of the things we have to address is sort of this reliable and safe operations in proximity to humans. And I show a cartoon here of a Roomba. I'm not sure if anyone knows what that is, but it's about this big around. And it's a little thing that'll sit around and vacuum your room. And there's a picture here of one sitting here, and there's the kid with his parent in the back, and then the dog in the front. And it's a dog-friendly device. We'll just go around, bump into things, and hopefully nobody will get scared. But when you got a device that's about that big and not moving very quickly, right? Safety in near humans isn't that big a deal. It just bumps you into you, and you don't feel that scared about it. Well, one of the things I did in the past was work on the Grand Challenge. And that vehicle number 79 is a 6,000-pound Land Rover going about 30 miles an hour, okay? So the closest I ever got to that was the other side of a concrete barrier, okay? I would never want to get anywhere near it. Nowhere like the Roomba situation where I'm just sitting there watching the thing drive around me, okay? So safety in the proximity of humans, when you're talking about large vehicles of this size, that's certainly one thing. Of course, when you start moving into UAVs, flying much faster and also much more energetic, that's another whole level of difficulty we have to address. So one of the things we've been looking at MIT is actually how to take the Grand Challenge technology up there and actually have humans in the loop. And I don't know if you can see it, but there's actually humans standing right here. The shadow is probably about as bad as it could be for you seeing that. But there is and so that's actually it's a sergeant in the, oh, thank you. First one? Yeah. So I don't know if that's me causing it to ring, but it sounds like it's ringing to me. But so there's a sergeant standing here, and she's interacting with this robot. So we've taken this technology and now mapped it to the point where you can actually have a human standing next to it. You can actually be driving the thing around and then decide to get up and walk away. And trying to reach that level of capability and that level of operation is key. But the key words that stand out here are operator confidence and trust, right? If you actually want to get to the point where you have safe operations in the presence of humans, they need to be able to trust this robotic system or this UAV and not have particular issues in terms of its operation. And you think ultimately about what we have, how these UAVs will be flying, it's the air traffic controllers that you have to basically have that trust and confidence. And so developing interfaces that will give them confidence in what these UAVs are doing is particularly challenging. Now, here's a particular example. AFRL has a program called Terminal Area Operations, and I'll blow this cartoon up in a second, but basically what they want to do is avoid the normal operations of sort of this is how we operate UAVs when they land. You close down the entire airport, you land the UAV, you go over and you grab the thing and you escort it back. Right? There's basically that paradigm they want to get rid of and move to a paradigm where the UAVs land at the airport and operate just exactly like a human-powered or human-piloted airplane would. So they want pilot-like behavior on approach, landing, and taxiway. And to do that, there's some of the key technologies that need to be addressed, right? You can imagine if you ever listen to the intercom or you're a pilot yourself and you know what it's like, there's short clip speeches of words that are being passed back and forth, and you basically need to have very advanced verbal and speech skills to be able to understand exactly what's been said. And one of the key phrases that come out is you need to be as interactive as necessary, but not annoying. And of course, there's always that cartoon of, press 2 to be annoyed if you're actually phoning a robot on the telephone, and it's just it's just bugging you, constantly asking you questions. It's like, leave me alone. You can't have that when you're dealing with an air traffic controller. You need to be precise, clear, and understood. And one of the other things is when you land, you've got to understand what's going on. You have to understand the other traffic. You don't necessarily have the sensing that tells you what's going on in the terminal or in the taxiway. So you need to be able to understand as you listen to the other flow of traffic or the verbal speech between other planes and the air traffic control exactly what it is that the other airplanes are doing and then be proactive about it. You don't just be reactive, but actually anticipate the fact that there are other vehicles flying around. So developing any kind of robotic system that's capable of doing this, but in particular UAV, a very complex device that's able to land and actually operate in a domain such as this, that basically gets very complicated. So basically what they want to do is to have you be able to operate in this very dense traffic flow and then land and operate exactly the same as a piloted airplane would. So what that means is that we also need sense and avoid for obstacle avoidance. So that brings now the next sort of layer of technology that needs to be thought about. So you then get into sense and avoid. And in looking at I can't remember where I got this picture. Most of these pictures came from just online. But this picture was sort of identified as, see how hard it is to find the airplane in this picture? Well, of course it's not. That's the airplane right there. And so it's actually quite easy. But I guess the argument is if that cloud happened to be sitting on top of that airplane, it would have been very difficult to figure out what was there. And so the point is that in terms of the sensing technology for sense and avoid, there's passive things that can be used. So LiDAR and vision, very standard robotic technologies. And then there's the cooperative ones that can be used, which are TCAS and ADSB. Just as, I don't know if it's going to work or not, but this is actually a shot that I have from my airplane. It turns out we're catching up another airplane. It's right there, but I don't think you can even see it. And this is just one of those particular instances where it's very difficult to see other airplanes that are right out the horizon line. And it turns out to be white on top, so it's just actually very difficult to see. So it's just an example of the fact that when you're doing non-cooperative and you're using local sensing, it's actually a very challenging vision processing problem, okay? And if you have LiDAR, that's great, but what kind of coverage do you have with LiDAR? And do you have 360 degrees? Probably not. You've probably got a very local sensor right in front of you. If you go non-cooperative, that's great, but now you're dealing with infrastructure, and infrastructure costs money, and if you want to do this low cost or relatively low cost, that's fine. And of course, then it begs the question, does everybody have it? And if you don't have it, then what's the point of it? And then there's just a basic reliability question and then a cost question. So all of this, and again, great progress has been made by the FAA and by FRL in terms of developing these systems. But when FRL talks about doing a UAV flying in the national airspace, they're talking about having both of these non-cooperative sensors and both of these cooperative sensors. And that's a very expensive proposition for every UAV that would ever fly to have all four of those. And that's just for the sensing. When you get to the actual response, again, there'll be cooperative, non-cooperative responses. The cooperative response is when we would negotiate on, okay, I think there's a problem, you go left, I'll go right, and we won't hit each other. Well, actually, I think we would hit each other if we'll both go left, and we won't hit. But basically, you have to make that decision. TCAS does that, and it's a very great system, but that tends to be more local. When you move into the further sort of longer range type of decisions, you then, that ADSB will be able to support. That would be great, but you need to be able to make sure that any decision you're making doesn't lead to this logjam where you create a problem for someone else, and you basically just hand your problem off to someone else or some other UAV or airplane that's flying. So you want to be as efficient and timely as possible, but you basically want to make sure that you stay within the FAA flight modes and deconflict all the other traffic that's around. So like I say, you just can't go and cause a problem for someone else just because you have an issue. So there's a bunch of issues that need to be resolved here. Some of the sensing level, I think a bunch of infrastructure and cost issues. Progress being made, great progress being made here, but I think going down a cost path that's different from what most UAVs will be able to support. And then I think there's some technology required here to enable a robust solution to the deconfliction problem. Some of the other challenges in terms of single vehicles, again, any robotic vehicle is going to have a problem. I'm going to have to play that video again. And the kinds of problems that you have, I say you're ubiquitous to all of them, so I work with many different kinds of robotic systems, and these kinds of issues come up. You got robust inference, which is the sensing problem. You got robust planning and control, planning under uncertainty, and then just the issue of integrating perception and planning together. But some of the issues that are specific on the control side to UAVs have to do with the flight control. And so this is actually a video from a friend of mine, Dave Voss, who's now working at Rockwell. And at the beginning of the video, if we go back, you'll see that piece of the wing just blows off. So this is actually a UAV. It's a replica F-18 scaled down size. And they purposely just broke off part of the wing and then wanted to demonstrate that their adaptive flight control could maintain stability of that vehicle. It's a very impressive flight. It actually just flies around for a while and then comes in and lands. And so that's a great thing to be able to demonstrate. And so recently, NASA has also been doing some work. This is a video shot from just last summer. And they're actually taking a scaled-down version of a 757 and driving the thing purposely driving it into a stall, which I think you see happen. and then they actually then are doing a recovery. And so again, there's some advanced adaptive flight control work that's been done by UC on this work. And then there's a bunch of things that I know Boeing does. I just grabbed this one. It's the one I think I can talk about the most. But basically what they were flying here was this autonomous helicopter, and they were just demonstrating how with the payload that they have here for, they actually had to rotate the thing around, and so that required some adaptive flight control as well. So again, all of these are just demonstrating the very good progress being made. With these kinds of vehicles and this kind of flight control, but basically more work is required. It's specifically to ensure that we can guarantee that these vehicles won't leave a safe flight operating volume. We need to be confident, if we're going to be able to try to convince someone like the FAA that we know what this vehicle will do under any situation, we need to be able to be confident that what the safe operating volume of that vehicle will be. And in particular, you'd want to be able to ensure that this thing can do a panic landing. You can imagine a situation where if there is a problem with an airplane and there's a pilot in the airplane, they might detect the problem, identify the problem. If you've still got some degree of controllability, you might be able to get the vehicle down, keep it horizontal, and then actually land it somewhere. But you think about the sequence of things that the pilot would have to go through. The key one would be, in fact, just identifying a safe place to land, a relatively safe place to land, both for you and for the people on the ground. And again, that goes back to the perception problem. Very challenging problem to do that in a stressful environment. Pilots are relatively good at it, much better than a standard vision processing tool would be. So there's some perception challenges, but also just the safe flight control volume. So again, great progress being made on manned vehicles, unmanned vehicles, but again, we need to be able to demonstrate that we have full capability of these vehicles over the entire flight volume. There's just more work required. And this really gets me to some of the core issues that exist for these vehicles. But basically, you need to do the robust fault detection and isolation just to ensure that you have acceptable risk without driving up the cost and the need for triple redundancy, which would be, again, a standard way of building a robust vehicle, but cost intensive. And so then I think this is probably the most important of the challenges that we face. That basically what we're building, there's a safety critical system. You're going to have autonomy algorithms that are operating in a very complex domain, and that doing verification and validation to be able to certify the performance of that software is one of the key challenges. And I'll bring up some quotes in a second to sort of hit that point home. But again, as academic, you might prove a theorem, and you're guaranteed that this theorem works. You do a MATLAB simulation. Maybe you try to do an experiment in the lab. But basically what we're talking about here is not just the implementation, but also being able to verify how your implementation, hopefully you've implemented it right, but also be able to verify how it works in a complex domain that's interacting with it. And again, when we were doing, the most complicated thing I worked on was the Grand Challenge vehicle, and we did a lot of simulation work because it is very hard to do this analytic verification. But the number of trials you would need here is just going to be prohibitive. So there is a lot of work going on standalone sort of software V&V. It's hard. There's some academics listed here that are working on it. But basically, when you get to a V&V of a system connected to the stochastic environments that we're thinking about here, that's going to be very hard to the point where it's, you're basically now working with an infinite state dimensional problem. And the question sort of begs the question, is this even possible to do with even if you forecast in a really, if you think about all the computers in the future in the world, if you took all of those and then use them, is it even possible to do? It's just a very, very hard problem. And so you then get to the point that, absolute V&V is probably not going to be possible. But there's some level of sort of confidence you need to be able to achieve so that you can then, again, convince the FAA that you understand where what this vehicle can do under many, many situations and many failures and interactions with sort of the stochastic world. And I'm not exactly sure how many nines of confidence you would need to be able to do that. Ideally, you'd have an infinite number, but basically this is, 6 or 7 is traditional for aerospace vehicles. If you're going into space, it'd be more like, 10 or 11 nines of sort of confidence. I think for a car, it's like 3. And so I think for even doing V&V for cars, is a difficult thing to do for the software, but for doing it for aerospace vehicles, when you need to get up to the 6 or 7, is going to be challenging. So just to hit this home a little bit harder, I don't usually put up paragraphs of text in the middle of a talk, but if you're interested, this is the report on technology horizons that came out last summer from AFRL, and I think it's actually part of AFOSR, but it maps out the Air Force's vision of the future. And there's some very, very telling quotes in there, and I highlighted them as best I could. but certifiable trust and autonomy through verification and validation of the near infinite state systems that result from high levels of adaptability. Basically, they see that as a limitation. I think the one I put down here in red is certifiable trust and autonomous systems is the single greatest technical barrier. Okay? I mean, and so I don't necessarily work exactly in this field, but you can imagine an entire field of control systems scouring this book saying, okay, what do they say about us? What do they say about us? And you get to this quote and go, yippee, right? I mean, this is it. Now just start throwing money at the problem, right? But the question is, will more money actually solve this problem? I mean, it's a very, very, very hard problem. And so there's some real hard challenges that need to be faced by the community to figure out how we're going to do that VMV and how to get that level of confidence in the execution of these vehicles. So moving on, if you go back to what Suresh had in his paper, there was sort of the first, I copied them here just so I could point at them. Many of this first 4 or 5 are about the single vehicle, and I think we've covered it. And VMV, holds for all, single vehicle, multiple vehicles. So all of those comments will pertain to the multi-vehicle case as well. But if you start moving up this chain, you get to 8, which is distributed control, 9 is sort of strategic, and then 10 is fully autonomous. And I thought I'd just make some comments about levels 8, 9, and 10, just because those are the ones I personally have spent some time working on. And so there is significant work on centralized planners. People have been moving more towards decentralized planning. And again, the distinction here is primarily on the amount of information that is assumed between the vehicles and what their actual objectives are. But in my experience, what I've noticed is that a lot of techniques assume essentially an information consensus, which is essentially getting to the point where, so the consensus is like a gossip algorithm. Everybody's talking amongst themselves, trying to come to consensus or agreement on what the state of the world is. So by doing information consensus, you're basically trying to get everybody on the same page about the situational awareness. A couple of issues. One, this can be slow. The rate will depend on the network architecture. People have been studying that, but the net result is that it can be slow. It can actually be very hard to accomplish and actually finish in a dynamic environment because new information keeps coming in. You're trying to come to consensus on something, and somebody keeps learning something new, and then it takes a while for that information to propagate through, and then you start getting confused about, well, is this in agreement with what I had before? And so you have to start dealing not just with the information, but the uncertainty in the information, and so the whole thing begins to snowball, and it gets quite complicated to do. So it's hard to do, but it also is sort of not obvious that all of that global information is needed by everybody. If there's people that are pretty far apart, do they really need to be having the same type of global information? So I think in terms of technical work here, what's needed is more of what I would call a neighborhood-based or hierarchic consensus approaches, techniques that allow you to look at a neighborhood and make sure these objects or agents are in agreement, and perhaps not necessarily in full agreement with this other set of agents, but in agreement as much as is necessary for whatever the task is that we're trying to accomplish. And so there's some technical work required there to address those specific types of consensus problems that are different than before. Another thing that I've seen in this trend is that a lot of the techniques end up being highly synchronized, or a set of highly synchronized operations across this team. So it's supposed to be a distributed planning system, but basically everybody's essentially moving on the same heartbeat signal. And so there will actually be a global schedule that tends to be instituted. And typically what you'll see is that nobody will actually mention this is the case. The theorems won't say anything about it. The MATLAB simulations will just implicitly enforce it, and you'll never check it or never even notice it. But it's actually when you go and start implementing these things over a distributed network, that's when you would begin to see how many minutes do we have left? This is 5. Is it? Okay. Couple of minutes? All right. Okay, couple of minutes. So what we've been trying to move towards at MIT is actually what is a more asynchronous version of it. So recognizing that this is a problem, and there's a fragility that typically happens when you have this heartbeat signal required. It slows things down. It's a very fragile implementation strategy. So we've been more moving towards an asynchronous planning strategy, and we've ended up with this technique, which has a very weird symbology. It's ACBBA. It's asynchronous consensus-based planning algorithm, but it focuses on consensus on the plan, not the information. And so there's benefits of this technique in terms of being asynchronous and think about the plan, and so it addresses both of these issues up here. And I'd invite other people to take a look at this work and maybe comment on it and send me an email if you have any questions. In terms of strategic planning, what I might do then, given that I've been told that I have 2 minutes instead of 5, is skip this part. But basically what we've been thinking about is, let me just jump to here. So at the strategic level, what we've been thinking about is very high-level planning. And typically what we've found is that these plans are based on models. They're model-based planners. So they make assumptions about the way the world will be. You create a plan, it looks great, it optimizes some cost function, you execute it, you run it forward in time. But the difference between what you're expecting to happen and what actually happened tends to be different. And as a result, what you need to have is basically a reflection or look back and do a learning exercise. So what we've been actually trying to do is to integrate the cooperative planner, a technique that a lot of people have been developing for actually doing the planning of these multiple agents, but embedding a feedback loop and doing learning. And in particular, what we're trying to learn is how to plan better. And this integration of planning and learning, I think, is the paradigm for the future and the way to move forward. All right, last comment. About level 10 then, if you're going to fully autonomous, right, and by their definition, that means there's no humans in the loop, then, of course, that means you have to be very careful and very safe. It requires significant V&V and much flight testing to get to that level of sort of no humans in the loop. But as I'm sure most of you are aware, even though UAVs are cheap, the operation of them is not. They can be complex and costly to actually execute outside. So one of the challenges then is how to effectively demonstrate these kinds of technologies in the lab environment that might enable you to do some of this validation. You'll be validating different things, but what you're trying to convince yourself is that you can validate something. So that it's really trying to understand the V&V process and say, if I'm in this lab and I have a stochastic environment, can I V&V that this algorithm works as well as it should? Okay? And so that's what we've been trying to work towards. We developed Raven, which I've talked about in previous trips here, but basically it's a motion capture-based environment. It gives you GPS indoors, and what it allows you to do is testing in a controlled environment, which is very nice. There's currently 3 feet of snow in Boston right now. Very hard to fly a UAV outside in that kind of weather. And so being able to fly at 4 in the morning whenever grad students are ready to work, and we can do multiple vehicles basically whenever we want. And it avoids the logistic problems and allows us to do a lot of rapid prototyping. I think I've shown this video before, but this is just an indication of the kind of capability that we have. So it's a kind of an old video, but basically we're able to fly in that room about 10 UAVs at once. Now, this is a great deconfliction. They all just have a little box, and it's like stay inside that box, and as long as you're inside that box, there's no conflict. As soon as they start moving outside that box, we'd have chaos. So our space isn't big enough. I know that Suresh is planning to build a space that's bigger than this, but the point is that you have a vehicle that can fly exactly, these are helicopters, but you can fly them basically exactly as you would fly them outside, and the only difference is they're not getting GPS signal, they're getting Vicon in the case that we're using here. So the point is that you can now execute them and operate them with software just the same way you would as if they were outside. So one of the things we were thinking about was, is it possible to replicate the important pieces of the national airspace, and in a big enough flight volume, you can actually fly airplanes around and actually have them little airports and fly them from one place to another and do all the deconfliction that you would normally do in a traditional operation outside. So just to summarize then, there's great potential for the UAVs in the future, but the significant technical work remains. In particular, some of the highlights then are just the flight control adaptability to numerous failures, the decentralized asynchronous multi-agent planning algorithms to ensure that the capability is there when we finally are able to fly all these vehicles in the airspace, and then the VME of the complex algorithms in complex environments. And one of the things that I think is becoming more and more clear to me is that much work is also required to make sure we address all the legal issues, and I think that requires a much closer coordination between the lawyers and the engineers. You need engineers that know how to talk to the lawyers, and lawyers that know how to talk to engineers. And just in terms of acknowledgments, I try to reference the pictures and figures when I use them, but there was a bunch of different pieces of work that I was looking at while I was making these slides. And most of what I've shown here is just available on the web and downloaded. And with that, I will stop. And thank you for your time.
Thank you, Dr. Howe. Due to shortage of time, maybe one question I'll allow. Anyone? No one. Yes, please.
When you're considering the obstacle avoidance of these UAVs, do you consider only solid obstacles or any disturbance in the aerodynamic atmosphere?
It sounded like sorted, but I wasn't sure. Well, I think in the obstacle avoidance world, there's terrain avoidance, there's avoidance with other vehicles, and basically obstacle avoidance with sort of things that are non-terrain, like buildings and trees and things like that. And I think the obstacle avoidance has to address all of those. certainly the work we've done has looked at terrain and also things like wires and poles and trees and buildings and so on. So I think it's addressing, it really has to address all types of obstacle avoidance. So I'm not sure if I'm answering your question, but the answer is you have to do it all, otherwise you're going to hit something.
How do you consider that the modeling of the whole UAVs?
The modeling of the airspace? Or
the modeling of the atmospheric disturbances?
Well, I mean, there is going to be a wind, right? I mean, if that's the disturbance you're thinking of, and that's a very hard problem. I mean, there are traditional wind models, but they're only good on average, and so.
Civil aeronautics models are available.
Yeah. Yeah. No, there's certainly models available, and I think you would have to use those. But I think a lot of it would have to be done based on local estimation of the wind effect. And particularly when you get into things like if you're in close proximity to buildings and other things, it's a very turbulent environment, very difficult to model. And so you would just have to embed a degree of robustness to the planning algorithm and actually try to be confident that, under all possible things that you might expect in the wind environment you're in, that you're still going to be safe. I mean, there's no hard and fast rule as to how you would do that. It's a hard thing to accomplish.
Thank you, Dr. Ho. He has beautifully explained how to achieve the level 10 autonomous operation in the UAV, especially when we enter into civilian airspace. And all of us, we know that in India, we still try to operate it at level 4. But the important issues of sense and avoid with the cooperative, the targets are non-cooperative, and what are the problems associated in finally giving the clearance to the vehicle by doing a lot of work on the ground. Due to shortage of time, we didn't allow him to fully present all the details, but if any of you have any more questions, you can interact him with during the tea session. Thank you, Dr. Ho.